This is problem 80 from chapter 17. The two blocks A and B have a mass of m sub A and m sub B respectively, where the mass of B is greater than the mass of A. If the pulley can be treated as a disk of mass capital M, determine the acceleration of block A, neglect the mass of the cord and any slipping on the pulley. We've seen this problem before. This is called an Atwood machine. And back in Physics 161, if you used spiral physics, this was the ingenious engineering student who wants to get up to his dorm room and designs a device and puts a mass on the other side of the rope which goes over the pulley and is pulled up to the dorm room. We solved this problem different ways in Physics 161. Today we're going to see a new way of solving this problem using equation 1710. And equation 17 says the sum of the moments of the external forces acting on the object about a point P is equal to the sum of the kinetic moments about the same point. I'm going to use point C, which is going to be here. So the sum of the moments about point C is equal to the sum of the kinetic moments about point C. And I'm going to do this for the whole system. So the mass A and the pulley and the mass B. So point C is the mass center of the pulley, but if I look at the whole system here, that is not the mass center of the whole system. So I'm going to call it point C. Instead, if I use equation 1710, I need to draw not only a free body diagram, but a kinetic diagram as well for summing up the kinetic moments. If you go back in your book to where they talked about equation 1710, this is on page 425. They show you how to draw the kinetic diagram. You do the mass times the acceleration and also the moment of inertia times the angular acceleration. So this is on page 425. On my kinetic diagram for the system, which is A and B and the pulley is rotating, and since the mass of B is greater than the mass of A, it's rotating this way, and that is the moment of inertia times the angular acceleration. Then I need the mass times the angular acceleration for A. A is going upward, so that's the mass of A, times the acceleration. And B is going downwards with the same acceleration, but in the opposite direction. So mass of B times acceleration. And my vectors here show the direction. So that's my kinetic diagram. Now I'm going to draw my free body diagram. Since I'm summing up the moments about point C, the forces which are acting on point C are not going to contribute to the sum of the moments of the external forces because they're acting right at point C, but I can draw them anyway. So I have this string which is attached to the pulley here that exerts a force upwards, and I have the force of gravity going downwards. Then I have mass A. This force of gravity which is going downwards is just for the mass of the pulley, so that's a capital M times G. Then I have a force of gravity acting on mass A and a force of gravity acting on mass B. So now I can use equation 1710. Oh, before I do that, let's go to the back of the book and figure out what the moment of inertia is for the pulley. So in the problem we are told we could treat the pulley as a disk. For the thin circular disk, for the axis Z, which goes through the mass center, the moment of inertia is 1/2 mr squared. So the moment of inertia about point C for the pulley is 1/2 times the mass of the pulley times the radius of the pulley squared. Okay, now when we find the moment, we do the vector R crossed with the force. The vector R goes from point C to where the force is acting, and since we are doing the cross product here, it's only the perpendicular component of that vector which is going to contribute. So when I do the moment for the force of gravity on A, that vector R from here to here has a magnitude of r. And if you go all the way from here to here, the component of that vector, which is going in the vertical direction, does not contribute when you do the cross product. And when I do r crossed with the force, that's pointing upward, so this is going to be positive, and it's r m a times g. When I go from here to here, for the force of gravity acting on point B, that's the same distance, r cross the force of gravity acting on point B, that's going to give you something pointed in the negative direction. So this is the sum of the moments for the external forces for our free body diagram here. Then we have to do the kinetic moments for the kinetic diagram. So when I do that, for the mass times the acceleration for A, when I cross that with the vector r, which is the same as what I had here, going like this, that gives you something in the negative direction. So this is, whoops, r times ma times the acceleration. And then if you do the vector r crossed with the mb times a, that's going in the negative direction. Oh, this one was supposed to be going in the negative direction. So if I do r crossed with ma times the acceleration, that's negative. And this is also negative. And then I have my moment of inertia times the angular acceleration. So that is plus 1/2 times mr squared times alpha. Then I want to relate the angular acceleration to the acceleration. If you look at a point on the pulley here, the acceleration of this point is related to the angular acceleration by alpha times r is equal to a. They asked me to find the acceleration of block A, and so I'm going to replace this alpha with a over r. And then I should be able to solve. So if I do that, then if I put that in here, every term on this side has a in it, so I can just pull that out and divide by what's left, and I get a is equal to, on the other side I had rmag minus rmbg, then divided by, pulling the a out leaves me with a minus r ma minus r mb, and then here the angular acceleration is going this way, so since it's going this way, this is actually negative, so this was supposed to be negative, so that's minus 1/2 and when I put this in here, that would be r times a, so this is just times r here. Then I can cancel a lot of things out, so r, and then everything in the denominator is negative, so instead I can write this as, let's pull out the g also, and switch the signs in the numerator and the denominator, so this would be mass B minus mass A over ma plus mb plus 1/2 the mass of the pulley. And it makes sense to write it this way because we know mass B is greater than mass A. So this is our answer. And there's another way to solve this problem. If you just wanted to look at the pulley itself for the system, you would have a force acting down on this side and a force acting down on this side. Those forces would be the tension in the rope here and the tension in the rope here. So if you did this to solve, you'd also have to do a free body diagram for mass A and for mass B. And you could do that to find the tension in the rope here, and I'm not going to solve that, but you can just by doing Newton's second law. Figure out that the tension on this side is the mass times g plus a, and on this side it's the mass of B times G minus A. And the reason that these forces are different is because in this problem our pulley has mass. And if I do that, then I can do the sum of the moments about point C for the pulley is equal to the moment of inertia about point C times the angular acceleration. Actually now I can call that G since that's the mass center of my system. And so on this side I would have R cross this force here, that would be positive. So that's R times MA, G plus A. On this side, R cross this force, that would be negative. So that's minus R MB G minus A times the moment of inertia for the pulley, which is 1/2 mr squared. 1/2 mr squared times alpha. Alpha, though, is A over R. So let's do that instead. And then this. And that cancels. It's an A. And then, well, I have an R here, here, and here, so those all cancel. And then if I solve this for A, let's see, this would be MA times G plus MA times A minus MB times G plus MB times A is equal to 1/2 the mass times A. So this and this and this term all have acceleration. I think I did the same thing here that I did earlier. And for this angular acceleration, since it's going this way, this is supposed to be negative. So angular acceleration going this way means it's the negative direction. So that should be negative. And then if I solve for A, I can bring this over to this side and this term over to that side. And that would be MB minus A times G. Bring all this term over here and then pull out the A and divide by what you have left. And that's MA plus MB plus 1/2 times the mass. And there we have another way of finding the solution.